First, let's try to understand a little better how this will be biased, because so far I kept saying, I kept showing an open loop op amp at the transistor level, and I kept saying that yeah, if you put it in feedback, it will get biased. Okay. So, let's see if those things really happen or not. Okay. Or how they happen. They will happen, but how they do. So, first let's go back to the single stage op amp. So, now this, if everything is perfectly matched, this voltage will be the same as that and all transistors will be in saturation, but there is zero chance of that happening. The slightest mismatch will drive it out of saturation, but that is also not very relevant, because we would not use an op amp like this. Okay. So, an example of how we use it is that. Okay, we place some feedback, and for now I will take this unity feedback. This is what kind of a circuit is this? This is just a buffer, right? So, ideally V naught should be simply equal to V I. Okay. So, what should I do to this? What should I connect to what? This is the plus terminal of the op amp, this is the minus, and this is the output. So, I have to connect the output to the minus terminal. Okay. Now, of course, you won't be applying VCM here. So, let us say you apply VCM here and see how it is biased. Okay. Now, what happens is that there is feedback. Okay, there is feedback kind of around every transistor. Once the op amp is in feedback, every stage of it is in feedback. Okay. So, this current mirror tends to make that current the same as that one. Okay. Now, let us say that this output voltage is some VCM plus delta V. What happens then? So, if this happens, the current through M2 will tend to be more than the current through M1. So, this will be I naught by 2 minus some delta I, and this will be I naught by 2 plus some delta I. Okay. And M3 and M4, you expect that this will be, what is the current through M4? I naught by 2 minus, no, due to the current mirror, what is it? This current will get mirrored. So, it will be I naught by 2 minus delta I. Okay. Now, this difference current will flow through some parasitic capacitance. Okay. And how much is that? Which way is it flowing? 2 times delta I is flowing that way. Okay. Now, let us say we did not have this feedback connection. What would happen to this voltage? It will go on falling. Let us say this was connected to something, it will go on falling until M2 goes into triode region, and eventually M0 also will probably go into triode region or something. Okay. But if we have this feedback, even if you start with VCM plus delta V, that will no longer be the case. It will fall down and eventually reach VCM. Okay. Now, even if the transistors are mismatched a little bit, let us say M2 has a slightly higher threshold than M1. What will happen is, because of this feedback action, this will go to something slightly higher than VCM, so that the currents are still balanced. Okay. So, because of this feedback, this is the same as when we had drain feedback and so on, right. We can't or in a CMOS inverter, we can't bias like this. Okay, this voltage will either rise up or fall down, but when we have this connected like that, it will get biased. Okay, is this fine? Which one? No. What I meant is, let's say you start from, this is VCM. When you have it in feedback, you apply a voltage here. And let's say this started off with something other than VCM. What I am trying to show is it will get restored to VCM. Okay. So, if this started off as VCM plus delta V, then a current will flow through this parasitic capacitance in that direction, and it will tend to pull down this voltage towards VCM. Okay. So, that is all I am saying. So, now I mean, you must understand that every transistor here is in feedback. Okay. So, that is what I wanted to show, because we have discussed ways of biasing it. I mean, the purpose of the op amp is not just to bias, but everything will get biased. Okay. Let us say you somehow think of M1 as the central player, and the rest of the arrangement is to bias M1. Okay. So, one of the ways you could do this is by having a feedback loop like this with a negative sign, right? We have seen this. Okay. So, now you can think of the rest of this circuit . This is just a sort of viewpoint. I mean, if you were asked how M1 is getting biased, you can see that from the drain of M1, there is a negative gain amplifier. This M4 here is a negative gain amplifier. It is a common source amplifier, and this is just a diode connected transistor. It's basically creates a level shift. Whatever voltage is here, so that minus the diode drop will appear here. Okay. So, you can think of this whole thing as simply creating a feedback loop from the drain of M1 to the source of M1. Okay. This is fine. I mean, I am just showing you like how everything gets biased, that is all there is. If you take any transistor, there will be the appropriate kind of feedback around it. Is okay? So, now instead of this, let us think of M4 as the central player. What kind of feedback would you need? You have the drain and you have the gate. So, what sort of feedback would you need between these? Some positive gain. Okay. So, if you now look at the rest of the circuit, what does this do? This is nothing. I mean, this is not an amplifier. What happens is whatever swing is here, the same thing appears there. It just creates a level shift. Okay. I mean, small signal wise, it's just a resistor. Okay. And what kind of an amplifier is this? From the source to the drain. What is it? Common gate, which has a positive gain. Okay. And it has a diode connected load. Okay. So, essentially from the drain of M4 to the gate of M4, you have a positive gain amplifier. Okay. So, every transistor is a negative feedback. That is what I am trying to say. Okay. So, because earlier we sort of thought about how to bias transistors, and we saw that we needed certain kinds of gains around, between certain terminals of the transistors for it to be negative feedback and get biased stably. Now, we made an op amp and put the op amp in negative feedback, but it necessarily implies that all the transistors in the op amp, if you take them individually, they will be each in negative feedback, so that it is biased stably. Okay. This is fine. Now, later we will look at the two-stage amplifier, put it in feedback, and again you can see the same phenomenon. Okay. Now, again the goal of the two-stage amplifier is to realize an op amp, but you can take any transistor there and then see that it is by itself in feedback through the rest of the op amp. Okay. In fact, this may be a good time to, in the previous quiz there was this circuit, right? Was this in the last quiz or the one before? Something. You were asked to find the output resistance here. Yes or no? Yeah, some quiz. Okay. What was the output resistance? 0. Was it 0? 0. Why is that? Yeah. So, what happens is that if M1 is a negative feedback, okay, and the current through M1 is fixed, the current through M1 is I1, right. So, and I1, and also you are told that GDS is 0, right, that is lambda is 0, which means that the current depends only on VGS. So, now first of all it should be easy to convince yourselves that M1 is in feedback. So, because the conventional circuit for biasing M1 at a current of I1 was just to connect it that way, but we do not have to make a connection of that sort. What we can do is we can take any stage which has a positive incremental gain and connect it. Okay, the only thing is after we make the connections we have to make sure that all transistors are in saturation. Now, you can think of this whole circuit as again centered around M1, where you are trying to bias M1. Okay. And what is the stage you use for positive incremental gain? What is M2 from here to there? What kind of stage is that? It is a source follower. Okay. So, you can think of M2 as implementing a source follower. Okay. And you use that to bias M1. Now, clearly if M1 had lambda equal to 0, then its current is dependent only on the VGS. So, if the current is set to a fixed value by negative feedback, then the VGS has to be absolutely fixed. There is nothing that can change it. Okay. So, in fact, it is not even necessary for both lambdas to be 0. If the lambda of M1 is 0, this voltage is fixed. Incrementally, that means that the incremental voltage is 0 no matter what you do. So, that means that the resistance looking back is 0. Okay. Now, you can also think of the same circuit as a circuit for biasing M2. We had a circuit where we sensed at the source and fed back to the gate. What kind of stage did we need between the source and gate? A negative gain. Okay. Something like that. So, how do we get the negative gain? How do we realize the negative gain? Common source amplifier. Okay. So, we realize a common source amplifier M1, I1 and use that to bias M2. So, I mean the point is that M1 and M2 are in a single feedback loop. You can think of as M1 helping to bias M2 or M2 helping to bias M1. Okay. Okay, and this happens in the op amp also, or any circuit with many transistors in feedback. You can look at each transistor, it has to be in negative feedback. Okay.